Hello class, this is Major Barham. So last class we talked about planetary orbits and how these planetary orbits were not perfect circles, they were in fact ellipses. So today we're going to model some of those orbits by drawing ellipses and then calculating the eccentricity of them. So get ready, you're going to be doing some calculations. So an ellipse is a geometric shape that you should have learned about in one of your geometry classes. It's similar to a circle, only it's more oval, it's more stretched. It has two foci. This would be one focus, this would be another focus, and a constant piece of string that I linked around the two foci. And by stretching the string and following through, I can draw an ellipse. And now I'll just go to the other side, doing the same thing, and continue the shape. And what you should see is that it's not a perfect circle. It's a stretched circle. So this would have an eccentricity, which I can calculate by measuring the distance from the center between these two foci to one of the foci, and then measuring the distance from the center to the edge of the axis. Along this we call the major axis. So if I continued this and measured all the way to here, this would be what's called the semi-major axis. So the eccentricity equals the distance between the center to the focus over A, the semi-major axis. This distance from here to here, this would be A. This distance from the center to the axis is C. And if I put these two foci farther apart, what I've done is I've stretched the ellipse. Get back in there. I've made the ellipse longer and narrower. So that distance between the foci changes the eccentricity. So you're going to have some calculations to do in this lab. So this would be the semi-major axis, the distance from the center to the edge. If this were a planet, this would be the elliptical orbit of the planet. The sun would be at one of the foci. Here's the other focus, it's vacant. So the sun would be at the center of be the focus. This distance from here to here would be C, your distance from the focus to the center. This distance here, half of the major axis, is called the semi-major axis. And all of the planetary orbits are elliptical. Some of them are more nearly circular than others. As a matter of fact, a circle is just a special case of an ellipse. A circle is simply where both of the foci are in the same place. So if you could imagine both foci there, the way to draw a circle that would be a perfectly circular orbit, but that doesn't happen. All of the orbits are elliptical. So I have done several of these with data for you. as I said, a circle is an ellipse with both foci in the same location. It's a special case of an ellipse. So in this case, the distance between the centers, the distance between from the focus to the center would be 0. The distance from the center to the major axis, the semi-major axis, would be 8. 0 divided by 8, so the eccentricity of this would be 0. Eccentricity of 0 means that it's a perfect circle. None of the planets have perfectly circular orbits. So here is your first example. For this one, I have given you the data. So the foci were here and here. The distance from the center to the focus, this distance c, is 2 centimeters. The distance from the center to the edge of the ellipse, the center along the major axis, the semi-major axis, is 6 centimeters. So you're going to need to calculate the eccentricity by dividing the distance c by the distance a. That's one of the calculations I'm going to grade you on. So the second ellipse that I showed you, that I'm showing you, the distance from the focus to the center is 3.5 centimeters. It's 7 centimeters between the foci, so halfway between them is 3.5 centimeters. The distance from the center to the edge of the ellipse along the major axis, the semi-major axis, is 4.4 centimeters. So the eccentricity is c divided by a. Do that calculation to find the eccentricity for this ellipse. And then you're going to answer some questions. Answer some questions based on those calculations that you just did, and then we're going to apply that same formula to the eccentricity of the orbits of the planetary bodies. So we've got Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and Halley's Comet. So I've given you the distance to the center in this far right column. I've given you the value of c, that's the semi-major axis, and you're going to use the value of c and a. This is the a, this is c. You're going to use that to calculate the eccentricity for all of these. And then, based on your calculations, you're going to answer which planet has the most eccentric orbit and which one has the least eccentric orbit. So, good luck. Do your calculations. They should be simple enough. And see you in class.